Hi. As the title said, this content is considered optional for a lot of curriculum, both in high school and in undergraduate calculus courses. So, if you don't think you're going to need to have epsilon delta proofs and you don't want to worry about proving exactly why limits are capable of doing what they're doing, then you can probably skip this. However, I wanted to include it because when I went through calculus, both in the 10th grade and when I was in college, I hadn't seen any of these proofs, nor had I heard about them. I was under the same assumption that a lot of people were when they went through calculus, which was that the limit and then calculus was invented by Leibniz, or the calculus was invented by Newton, or there was a fight about it and they invented it and then this is what we do, and had never even heard about Cauchy. However, that's just not the reality of the situation. They went a long way and they laid the groundwork for what we did, but much like how we are taught calculus in an undergraduate or a high school level, they had a conceptual understanding that was actually pretty flawed, and that for well over 100 years, most mathematicians, while they used the methods that were developed, they weren't comfortable with them because they knew that they were using methods that very much had a trust me bro feel about them. And it wasn't until mathematicians like Cauchy came along and applied a very rigorous definition to what had previously been a very non rigorous usage that we were able to then prove that something that had become very foundational to science at the time actually did have the rigor necessary to be something beyond just, well, we're pretty sure this works. And that new definition is what we call epsilon delta proofs. The way these work is that instead of approaching the limit from the viewpoint of the domain and bringing the domain in close enough and then saying, well, we think we're close enough, so we're going to call that good, and here's the output. We set the range and we say we need to come within this close. We need to find some distance, and that's the epsilon. And if we can set an epsilon, then this limit does exist if there's a delta that can provide that epsilon. I'll demonstrate all of this and I'll show this with a visual, and when you see it, it does make a lot of sense. And when you see the definition, you'll understand what I mean when I say this is a rigorous definition that we can then use to do proofs, because it allows us to take what was just a conceptual understanding and turn it into something that is computational. And then what we're also going to do is show how we can prove all of those rules that we kind of just said these work from a conceptual standpoint. We're not going to prove all of them, that would take quite a while, and they do get a little bit mechanical, so we're only going to prove one of them, but we're going to demonstrate the methods that are used to prove them. Well, I say we're going to prove one. We're actually going to prove three, but two of them that we're going to prove are the ones that I had mentioned are a little bit trivial to prove because they're easy. They're what I like to call candy proofs, because the proof of them is you pretty much make your statement, fill in some variables, and then the proof is done, and you feel a little bit like a genius for having done it so easily. So if this is something you're interested in, be aware that this will be a longer video. This will be a little bit more like you're taking an undergraduate lecture course, because I'm going to go a little bit more in depth than I do for the rest of these, because this is material that might not be included in a typical calculus course. So where all of the rest of the videos in this series are meant to support a class, so I'm sure that that material will get covered pretty in depth in your coursework, probably over the course of multiple days, along with exercises that you'll do with the assistance of a teacher. This material, this might be one of the only places you see it unless you go do additional research on your own. So let's go ahead and get started. Now, the first thing I want you to understand when we're talking about these epsilon delta proofs is they don't necessarily change the way that we evaluate where a limit is. It's simply a way to prove that the evaluation of the limit actually does exist, or that the value we have picked for the limit is in fact the limit itself. So this is a method of proving that the conceptual concept, that idea of honing in or of moving into that value, does exist. And this helps us in those situations where before, when we had, for example, that sine graph where it simply was oscillating between values, this actually gives us a way of demonstrating something beyond, well, I looked at it and it looked like the limit didn't exist, so I'll just say it didn't exist. Using an epsilon delta proof, we could actually demonstrate, no, it doesn't exist, because we now have a criteria that it would fail. Okay? So in order to get to that point, though, we do really need to understand what the difference is between these, because aside from obviously the fact that this is a little more mathy, you might not recognize the important difference here. Okay? So the intuitive and conceptual approach will be useful for most students, especially when you get into using derivatives, because once you understand the rules of how to use the limit, the idea of how to find a limit is going to be something that, aside from the trickier ones, you may not have to fall back on as much, especially if you're not going to be going into a pure math field. But like I said, when I was in school, I didn't see these very much until I got into advanced calculus. And by that point, my professors thought I had already seen these. So I went from zero to having to, learn these very quickly in order to jump really far ahead. So, this might help some of you that will be going into those fields. Okay? Anyways, so the intuitive or the conceptual approach is the one that we've already discussed. I'll reread it again just to remind you, which is, let f of x be a function that's defined on some open interval that contains a, except perhaps at a itself. So some discontinuity, maybe a division by zero, or maybe an asymptote in the case of an infinite limit, right? Then let L be a real number, and if the values of f of x approach L as x approaches a, and x does not equal a, then we say that the limit as x approaches a of f of x is equal to L. Now that's perfectly fine. What we're saying is we're going to ride this graph along the graph, coming down, and we're going to check values, and if the value of f of x continually approaches a value, then we say that that value we're approaching must be the value at that point if we could get there. Okay? That's the conceptual idea, and sure enough, we use it for a lot of stuff, and it works, right? And I would be remiss if I continued to say that this was invented by Leibniz or invented by Newton. The notation is a very modern notation. The idea is a very modern idea. They used something similar. Leibniz used something called the infinitesimals. I don't quite remember what Newton's idea was. Neither of them got it right, because neither of them quite had a concept of infinity or quite fully had a concept of zero the way that we consider it now, although they were both getting a lot closer than any of the previous mathematicians had. Both of them kind of cribbed the idea from Archimedes, and I'm not sure where he maybe got the idea from, but if you go back and look at Archimedes' work with pi and with developing the formula for a sphere, you see that he almost created calculus back then, and he had even less of an understanding of the concept of infinity and zero. So, this was an idea that had been bumping around for many, many, many years, and it did take a couple of geniuses to kind of formalize it and bring it forward finally. So we were very lucky to have them, right? But the problem is, it still wasn't rigorous enough to actually do calculations to say why it worked. It did work, but it took over 100 years to say, yeah, okay, it works, but it still feels really kind of like, ooga booga, it's gonna just pretend. Let's just say we got there, And that's kind of the problem, right? And the big problem here is that with this definition, we're coming in at this from these two sides, and then we go, yeah, okay, I'm close enough. And we never really consider how close on this side do we have to be when we get there. Whereas with the rigorous definition that Cauchy came up with, we come at it from the other direction when we're proving it. Now, we still evaluate where that limit would be in the same kind of idea. We look at the graph, we examine the function, we assume, we estimate, we use all of our algebra skills to say this is where that limit should be based on the activity of the function, based on the activity of the graph. So all of that is still the same idea and is still similar. But when it comes to that point of going, yeah, but is it actually that number, and nothing weird happens when we really zoom in, like what happened with that sine function we looked at before, right? That's where this part comes in. Okay, so let's go ahead and read this one real quick, and I'll also explain the other very important difference here. Okay, so this one is, let f of x be a function defined on an open interval containing a except perhaps at x equals a. So very similar, effectively the same kind of wording. It's a little different here, but we could reword it to be the exact same thing. Okay, then the limit as x approaches a of f of x equals L if for every epsilon greater than 0, okay, there exists a delta greater than 0 such that if the absolute value of x minus a is greater than 0 and less than delta, then the absolute value of f of x minus L is less than epsilon. So what this says is that this limit exists if I can select some margin, some distance, any distance, okay? Because it's every epsilon greater than 0, meaning any real number, anything, okay? Any number in the range of that function that's greater than 0, okay? Any distance from the point you're telling me is the limit. So you told me what the limit is. Now I'm going to say, okay, hotshot, if that's the limit, then I want you to find me an x value that gets me within 5/1 millionths of that number. Okay? And that's what this is saying, that any epsilon greater than 0 that I pick, you should be able to find a delta where this will be true. X will not equal a, and if I take x minus a, it'll be in between 0 and that delta. Okay? So this sets a criteria, this sets a rule where we can find a relationship, just like the function is a relationship of the domain to the range. I now have a relationship that actually relates what was before just kind of a, if x is close enough, L is close enough, and we'll call it close enough. Now we say, no. There's actually a relationship where when you tell me how close f of x needs to be, if that limit exists, there will be a margin down here as well, okay? And what that lets us do is that lets us find that relationship. And so that means that we don't have to now try to find some calculation and go, well, yeah, but could you have gotten closer? Because if you remember, when we were examining it mechanically, we had the problem of, okay, but what if I picked the wrong interval? Or what if I didn't get close enough? You know, this says, well, it doesn't matter. It doesn't matter what interval you picked or how close you got, because I'm going to tell you what the relationship is. And so now no matter what number you pick, I'll tell you the relationship, so you can't mess up the interval, because it'll be, this number will automatically tell you what that number should be. And the nice thing here is I pick this one, it tells me this one, but I check it going the opposite way. So when we do these proofs, we select this, we find that, but then we test it by throwing it in the, so basically you come out from the back, you pick a number, you set the rule, that tells you what the front's got to be. But then to test it, you throw it in through the front to see if it works and gets you the answer out of the back. So you're kind of, it's like doing a double-blind test in science, okay? You tell it what the solution's going to look like. And then it says, okay, cool, well, if that's what the solution's going to look like, this is what I've got to put in to get that solution. And then you go, okay, so test it. And then you throw it in, and if you get that answer out, well, then that means it works, right? Which is how functions work in general, okay? And I know that's kind of a long explanation, but it's because I'm trying to take the rigorous one and explain conceptually why this rigorous one is important compared to what we did over there. Now, if you don't understand the graph here, the reason why I've drawn this f of x to the L and this x to the A, x does not get to A, right? But it approaches A. And this A minus delta and this A plus delta, that's not here. Except that it is when you remember how absolute value works. And we will look at that because you do need to have a pretty strong understanding of how absolute value interacts with inequalities in order to do these proofs. So we're going to look at absolute value and inequality next, and then we're going to look at an application of this proof using actual numbers before we jump in and look at one of these proofs in a kind of more generic one to prove the actual rules we did. So here we have the basic inequality and absolute value properties. These are the same properties, for the most part, that you've learned in your algebra classes or in your middle school classes when you were first learning about inequalities and absolute value. Over here, you just have your basic definition of the inequality with addition. So if I have A is greater than B, then if I add the same quantity to both sides, it doesn't change my inequality. And if I have A is greater than B and C is greater than D, same thing. My inequality will not change if I add my larger values and my smaller values. Down here, this is if I take some positive constant and multiply it to both sides, it will not change my inequality. But if I take a negative constant and multiply it to both sides, it will change my inequality. Okay? That's simply what this is saying because C is less than 0, so it's a negative. Okay? And then the one down here is that if I invert, or if I take the inverse of my values, it will also change my inequality. And you can use simple algebra to demonstrate this to yourself. Now, for the absolute value, most of these properties I assume that you'll know until we get down here to the bottom one. This one we will be proving in just a moment, okay? So the top up here, I've shown you this one before. This is simply the definition of absolute value as a piecewise function. It's very useful to take things like this and do this. You can do something similar with the square function. It's a little bit weirder there, but you can do it in order to help you when you're working with inequalities. And then here we have the product version, so it's just the absolute value of the product of the absolute values. The quotient, same thing. Power rule, same thing. Now, down here is where we get into the interaction with the absolute value, and this is where you're going to want to make sure you're paying attention to this. And for the most part, this is simply using algebra on our inequality when combined with the definition here as a piecewise function. Because when you think about this being two equations, we've got the plus version and the minus version, that's how we're getting this to put it together. Because if we have x is greater than y and negative x greater than y, but then we multiply it across, you get then that the x is greater than the negative y. And then you can put that together to get this. And then when we have the less than, that's where you get that x has to be less than negative y or x is greater than y. And if you're having a difficulty understanding exactly what those are, I would suggest draw it out on a number line and you'll see exactly kind of how that works when you think about the y being your critical values, and you are either going to be inside your critical values or outside your critical values. It's just a very nice way to think about it. Now, the triangle inequality, this one down here, is named this because we can demonstrate it, and we're going to prove it using algebra, but you can also demonstrate it with a geometric proof using the sides of a triangle. This is very crucial for a lot of the limit proofs because, as you saw, we're talking about using epsilon being greater than 0 and delta being greater than 0, but then we're looking at f minus L being less than epsilon. So we're going to have to be building chains of inequalities with addition and subtraction. And we cannot just take an absolute value and break it apart exactly. So we're going to have this theorem in order to do so. And it'll be nice if we know exactly how that works. Now, if you know how this works, obviously you'll be able to skip past this next part. For the proof of the triangle inequality theorem, I left up the absolute value portion. I erased the inequality portion, but we'll be referencing some of the rules that we used there. So the first thing we do is we break it up into 3 cases, because when you're working with the absolute value with a sum, you have 3 situations. Either both of your values are positive, both of your values are negative, or you could have a situation where your values are positive and negative. If both of your values are positive or both of your values are negative, then it's trivial because you have the exact same situation. You're adding. Because if both are positive, you're adding 2 positive numbers. If both are negative, you're adding 2 negative numbers. And it doesn't matter because whether I take the absolute value before I add or I take the absolute value after I add, it will be the same effect in the end. Okay? And you can demonstrate it yourself here because I add the numbers, I take the absolute value, it gets rid of the negative. I take the absolute value first. There's no negative here because these are positive, but same thing. And then I would add them. I get the same answer. When I'm using the negative version, I simply come over here and I go, oh, okay, well, it's negative, so I'm going to use the negative x. So when I take off my absolute value, I put the negative sign. Sorry, those shouldn't be there. There we go. I take off my absolute value, the negative goes here. I take off my absolute values, the negatives go here. So then I use a little bit of algebra. The negative comes out, or the negatives go in, and you see that they're the same. So you can work your way around. It ends up being the exact same difference, okay? And you can test that yourself evidentiarily, ooh, that's a hard word to say, with some values, okay? Remember, evidence is helpful to demonstrate that your plan or your idea works. It's not actually proof though, okay? And then if we look at case 3, this is why we need the proof, okay? Because this is the situation where we have opposite values. We have a positive and a negative. And in this situation, we have a true inequality. In the previous versions, it was equality, and equality is, trivial when you're talking about less than or equal or greater than or equal because the equal subsumes the inequality portion. But here, the situation becomes we actually have inequality. And you can, again, check this with yourself by simply picking 2 values, say 2 and 3. If we use a negative 2 and a positive 3, watch what happens if we plug them in. So if we take the sum and then the absolute value, negative 2 plus positive 3 is 1, absolute value ends up being 1. But if we take negative 2 and positive 3, take the absolute value first, that's 2 plus 3, that's 5. 1 is less than 5, which fits our triangle inequality. So we've demonstrated that, yeah, okay, it sounds like it works, but we want to prove it to ourselves now in the generic term with, variables, with something where we can say, pick any real numbers, and this should work. So we set ourselves up by saying, well, we have 2 cases, right? Because if we're going to be doing this, if we're going to be subtracting 2 numbers, then when we subtract those numbers, one is going to be bigger than the other, or they're going to be equal. Now, if they are equal, then we fall into here. But if the x is positive and the bigger number, we fall into here. And if the x is positive and the smaller number, we fall into here. Okay? So we get a positive value or we get a negative value. But that exactly fits our definition of absolute value. So we're going to apply the situation in case 3 that we've broken into, again, 2 more cases. So I guess technically we could say 4 cases. And we then apply our definition of absolute value. Now, if we're in the positive version, then that means our absolute value is equal to the positive sum. And if we're in the negative version, then our absolute value is simply equal to the negative sum. Not a big deal. When we distribute that negative, that's how we get the negative x and the negative y. Okay, I skipped a little bit of a step there just for the sake of being within the space I have. Okay, now the other thing we know is that a value has to always be less than or equal to its own absolute value. Similarly, a negative value always has to be less than or equal to its own absolute value. And again, this is a trivial proof. You can demonstrate it to yourself easily. You can also think it through easily by simply applying these three properties together. Okay? Because again, the equality property, equal, subsumes the inequality, and then the inequalities work with what we have. Okay? But now, if we take these and then apply the previous property of inequality, well, we have a less than situation and a less than situation. So if we add the x plus y, which is less than the absolute value of x plus the absolute value of y, we'll preserve that inequality. And we'll similarly preserve that inequality over here. Okay? So we know, and again, this is not a big deal. We know then that x plus y has to be less than the absolute value of x plus the absolute value of y. Not a big deal. And we know that negative x plus negative y has to be less than or equal to the absolute value of x plus the absolute value of y. But this is where the fun part comes in. We have this property that says that the absolute value is equal to y if and only if x is equal to exactly positive negative y. Well, wait a second. The absolute value of x plus y is equal to x plus y, and the absolute value of x plus y is equal to negative x plus negative y. So therefore, the absolute value of x plus y is equal to the plus minus of x plus y, which is less than or equal to absolute value of x plus absolute value of y. And there we go. So you can basically wipe out the middle, and we've got our triangle inequality statement. So we showed it to ourselves, demonstrated with evidence, but then we proved it. Now, what I want to point out to you is that this is actually very similar to what we've been doing with the limits. We had the conceptual idea, and we've demonstrated that it works, but in order to actually use it and rely on it, we want to be able to prove it. And that's what we're doing with the epsilon delta proofs. And it just so happens that we need to use this in order to work with the epsilon delta proofs. So, it kind of ties into each other. Here's an example of an epsilon delta proof. Now, this is a pretty straightforward proof, and it's one where it's pretty obvious when we apply our limit rules that we learned in the previous video. However, remember, the entire point of this is that we haven't proven any of those limit rules. And these epsilon delta proofs are how we are going to prove those limit rules in general. Now, I've picked this one because it is a very easy one that we can kind of work our way through. It doesn't require a lot of algebra, and it doesn't require, for example, the triangle inequality proof, which does get a little tricky to apply. Also, by not being too extensive of a polynomial, it's only first degree, it means we don't have to worry about doing multiple tests. We can simply do a single test. I will warn you that when you are working with these epsilon delta proofs, they can get a little bit complicated, which is why we like those limit properties that we learned in the previous videos, and it's why we prove those limit properties, so that we don't have to go through this process every single time, especially when we're dealing with more complicated ones. However, one of the reasons why we need things like these epsilon delta proofs is because those limit properties don't work with all functions, because sometimes we get complicated functions where those epsilon delta properties won't apply very well. And that is, of course, why we have things like the squeeze theorem and some of our other properties that we do utilize that we weren't able to prove because they're even beyond the scope of this course, and especially this video that's already getting a little bit long. So really quickly, I'm just going to kind of walk you through where the pieces are in the definition and in the proof, and then kind of the process that you follow almost every time for every single one of these proofs. Okay? So the definition again is that we have some limit that we have discovered in L, And then what we were proving is that for every epsilon greater than 0, there exists a delta greater than 0, such that when we have the x minus a less than delta, we have the absolute value of the function minus L less than that epsilon, okay? So in order to use this to prove the function exists, we need to already have our A and our L, and then of course our function. So we start by simply assuming that we do have an epsilon greater than 0. Now, sometimes you will work with these where there's a specific epsilon, and when that happens, we call those margin of errors, okay? In this situation, though, we're saying any epsilon greater than 0, and we're trying to find the relationship. So we do this, and then we set it up and we say, well, if it's any epsilon greater than 0, then that means we're looking at an x minus a, which is 3. So that means we have the absolute value of x minus 3 that's less than some delta, and we're looking for the delta, okay? And if this is true, then we should be able to find the f of x minus the L that will be less than that epsilon. Now, the goal is to make this part here, not the epsilon, but this part, look like this part, very similar to what we were doing earlier, okay? And in that algebraic manipulation, something's going to happen on this side with the epsilon. And if we get this side to look exactly like this side, then whatever is over here will be that relationship that we need for the delta. Okay? And this is, like I said, a simple linear inequality, or a linear absolute value. So it's pretty easy to go through and solve this one. And so we walk our way through. We don't need to do a whole lot of extra work here. We don't even need to break it out of the absolute value in this situation. So that's kind of nice. And we get x minus 3. We have x minus 3. So we're looking for a 3 epsilon. Meaning that if you pick an epsilon, then the delta we need to pick only, or can be as large as 3 times that epsilon, and it will work. So if you said, hey, I need to be within a tenth, that means that you could pick 0.3, and that would get you close enough, because you would come in within that margin of error, okay? So that's what we're looking for. So once we've found what we think will work, the way we prove that it works is we stick it back through our machine to see if it spits out our answer. If it spits out this product, basically, okay? So to do that, we say, well, we've got an epsilon greater than 0, and we're going to pick this to be our delta. So we take that delta, we replace it with the delta we selected, and we run it through, and we say, well, if that's our delta, where here we modified this side to get the epsilon, this time we're going to run it backward and try to get epsilon by itself. So we do that, but now this does not look like that. So now we need to run this backward and try to now modify this to get it to look like that. And if we can successfully do that, we've demonstrated that yes, that delta we picked does in fact produce the function we were looking for within that margin of error, within that region you told me we needed to find. So yes, this is pretty easy, simply using our absolute value functions. We divide the 3 over. It's not negative, so it doesn't change any of our signs. It's positive, so we can bring it into the absolute value, no problem. Divide it through, and we finish up. See, 3 divided by 1/3, we get the 1. We break it up to a positive 1 with the minus 2, separate it out, flip it back, 1 plus 1/3 x, 1 plus 1/3 x, that's our f of x, 2, that's our L, and we're done. But even this simple one, it's a little bit big. So it's nice that we do have those limit properties once we've gotten them proven, which is what we're going to do next. We are only going to prove the sum one, and you'll see the reason we're only going to prove the sum of the limits is because those also get a bit long. But I will say that every single one of them is proven using the epsilon delta definition. And now the moment you've all been waiting for, we're going to prove one of our limit laws. we're going to go ahead and work with the sum law because it's one of our fundamental laws, and it does require a little bit of cleverness, and it uses the triangle inequality theorem that we looked at. So we start with what we're going to prove, our statement of proof. And here it is that if we have the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m both exist, then the limit of the sum of the functions is equal to the limit of the first function plus the limit of the second function. So the proof begins the same way that our specific example began, and it's that we have some epsilon greater than 0 that exists, and we're going to look for a delta greater than 0, such that if the absolute value of x minus a is less than that delta, then our function, which is our sum, minus our L, which in this case is the L plus m, is going to be less than this epsilon, which for us is just any epsilon, just like last time. Okay? Now, because we don't have a specific L and a specific function, we kind of have to get clever. So we're going to use our algebra, but we're going to use our algebra a little generically. And in this case, what we notice here is that we have f of x and minus L, we have g of x and minus m. So we rearrange it and we get f of x minus L plus g of x minus m, which looks very much as if we're looking at the limit of f of x and the limit of g of x. So by the triangle inequality theorem, we can take this limit and say that this absolute value is less than or equal to the sum of this absolute value, which is very close to the limit we're looking at. It's just missing this epsilon. So now, if we can somehow relate this piece to that epsilon there, we'd be done. So is that possible? Well, we started by looking at this side of our proof. Let's jump to the other side now, and let's look at this side. And we're going to use the fact that our limits do exist in this next part. Basically, we're using all of the buffalo, okay? And that's what this next section is, this really wordy section here. And it's wordy because we have to kind of lean into a lot of these definitions, a lot of this understanding here. And so what we're saying here is that because we know that f of x and g of x, these limits, rather the limit of f of x and g of x exist, we're allowed to choose whatever epsilon we want for those limits. And so we're going to pick that specific epsilon to be this epsilon here divided by 2. Okay, awesome. And we can do that because this is the same a in all spots, right? So we're on the same open interval and we're approaching the same a, so that means we're within that same margin. And so we can pick an epsilon, and in this situation, by selecting an epsilon that's smaller than our original epsilon, that's going to give us a pretty big benefit. And by selecting specifically an epsilon that's half the size of whatever the original epsilon we looked at, that's going to give us an even bigger benefit since we're looking at doing addition. This is the cleverness that you get in this kind of art of proof, where you have to think about, what's my eventual goal? Like, how am I going to get rid of parts I don't want, and see if things fall into place, okay? So we go ahead and we say that because these exist, I'm allowed to pick whatever epsilon I want. I'm going to pick epsilon divided by 2, and I'm going to pick it for both of these. Both of these guys are going to be strictly less than that epsilon divided by 2. Perfectly acceptable because I can pick any epsilon because the limit has to be true for every epsilon, right? Okay, well, because they exist, then there has to be some delta 1 and delta 2 that are greater than 0, such that x minus a is less than delta 1, then this exists. And when x minus a is less than delta 2, this exists. Okay, but we have a slight problem. Small issue, just a little one. And that little problem is that, well, this is delta 1 and this is delta 2. And I don't care about delta 1 and delta 2. I need delta. But we fix that by going, see, this is for every epsilon, but this is a delta. So that means for every epsilon, I can find a delta that exists. So that means I just have to find a delta that works. I have two possible candidates here. So I'm going to say this delta will just be whichever of these two happens to be the smallest. Because if one of these two is the smallest, then automatically I'm going to fit the criteria for the other one. Because, think about it, if delta 1 is the smallest, then x minus a is smaller than delta 1. But if delta 1 is smaller than delta 2 and x minus a is smaller than delta 1, I'm automatically smaller than delta 2 because this delta 1 would fit in between these two. Simultaneously, if delta 2 was the smallest and I said that x minus a is smaller than delta 2, well, delta 2 fits in right here and x minus a is smaller than delta 2, so automatically I fit this criteria. So if my delta down here is the smallest of these two, by x minus a being the smallest, I automatically make both of these criteria true. So by this delta being the minimum of these two, boom, this is automatically true. So at this point, we found the delta. But remember, the second half of the epsilon delta proof is to go, okay, you claim you found the delta, now prove it works. So here you go. It's a little bit more sparse because it's a lot easier to work your way back around once you've done all the original work. So just a reminder, from the very beginning of the proof, we showed that our original statement through the triangle inequality theorem is equal to this statement here. We're going to be using that. Now, we showed that this exists. So now we're simply going to go ahead and add it together. So if we add it on this side and add it on this side, over here, epsilon over 2 plus epsilon over 2 is simply epsilon. And over here, well, it's simply added together, but from part 1, we know that we can reverse the triangle inequality theorem into here. But because this is less than or equal to this, we use the equality portion of it, meaning that it's still less than this epsilon, because it also retains that less than feature. So therefore, we know that this will never be greater than this. At most, it will be equal, which means it will retain that less than quality of this epsilon. So therefore, when the x minus a is less than that delta that we found, the minimum of the deltas that make these steps true, it will also make this limit true, thus proving our sum. Pretty elegant, pretty awesome. I did not come up with this proof, by the way. This is an old proof. Next, we're going to do a couple of the more simple proofs. We're going to look at the constant proof and the replacement proof, both of which are a lot faster and more straightforward than this one. Before I jumped in and did the proof, I wanted to give you a chance to go ahead and try it. So see if you can apply what we talked about with epsilon delta proofs and solve these two. And don't worry, I will show you the proof. I'm going to do it in 3, 2, 1. I hope you can see why I called these candy proofs at the beginning. They're pretty bite-sized and they're pretty simple. You probably looked at them and you were like, I mean, yeah, it's pretty obvious, right? But you can also see how they fall in line with the epsilon delta proof, because when you apply the epsilon delta proof, you see that even with these simple basic concepts, it does fall in line with the idea, because we're talking about, we look for an epsilon, and well, of course it's going to work, because since we're approaching that A, no matter what epsilon I pick coming towards that A, because x is approaching that A, of course I can find a delta, because the x is coming towards that A. So since I'm approaching that A this way, I'm going to find something this way, because that's what I'm doing, right? And it just means that any delta that equals epsilon is going to work, okay? And then when it comes down to my constant one here, we are assuming that the c, the constant, is just an element of the reals. That's just saying that, hey, c is not a variable, it's an unknown, okay? So when we put it into here, the way that our epsilon delta proof comes out is that we say our function c minus our L, c, but c minus c, because it's a real, that means it's 0. So epsilon is greater than 0, but wait a second, epsilon's always greater than 0. So because epsilon's always greater than 0, it really doesn't matter what your choice of delta is, as long as it fits the criteria that we picked a delta that's greater than x minus a. So any choice of delta that's greater than x minus a works, because epsilon's always greater than 0 in this situation, because it really doesn't matter where you pick, because it's always going to be the same, right? So I've gotten a little wordy with the explanation here, but that's because it's sometimes a little hard to explain the obvious, because it's so obvious. So if you made it all the way to this part of the video, then congratulations. You've effectively sat through a college freshman calculus lecture on epsilon delta proofs. Good job. As I said though, the reason I made this video, and the reason it's so long, and the reason I presented it the way I did, is because this curriculum isn't necessarily always included in the high school level, or even in the undergraduate level at college, and sometimes when you get to the graduate level, it's expected that you've seen it. So I wanted to make sure that it was available, and while I know that this information is available everywhere else, I felt that I would have been remiss if I didn't include it in this material for people that were looking for that stuff and happened to find it here. So if you are needing any other information like this, please do let me know. There is a lot more to cover in this topic. You'll notice that we didn't talk about epsilon delta proofs from the right or left the way we did with regular limits, and we also didn't discuss them and how they work with infinite limits, because there are epsilon delta proofs for those topics as well. And then in addition, all of the various laws have their proofs. You can look those up, and if you're interested, I don't mind going over those as well.